Good afternoon and welcome everyone to our second webinar of the year on isocyanate resins exposure monitoring. I'm Kelly Johnston, an Associate Professor at the University of Queensland. I'm the Director of our Masters of Occupational Hygiene program at UQ. I'm also a member of the AIOH Professional Development and Education Committee, and presenting today is Greg Manthe. I'd like to start with a welcome to country. We acknowledge and pay respects to the past, present, and future traditional custodians and elders of this nation, and the continuation of cultural, spiritual, and educational practices of Aboriginal and Torres Strait Islander peoples. In terms of an introduction to our webinar today, isocyanate-based polymeric chemicals are used extensively in mining and construction to fill cavities and reinforce or stabilise strata in the underground environment. Methylene diphenyl isocyanate, or MDI, is a common ingredient and is a known respiratory sensitiser and skin allergen, which can be inhaled or absorbed through direct skin contact. RSHQ has been investigating the adequacy of current atmospheric and biological monitoring techniques. Testing results have identified and confirmed the presence of unexpected organo-isocyanate species and variants of MDI that are not detected by current biological sampling or atmospheric monitoring methods. And Greg's presentation today details these findings and will discuss the sampling methodologies, interpretation of results, and recommendations for industry. I'd like to now introduce Greg Manthe. Greg is an Inspector of Mines, Occupational Hygiene based in Brisbane. He's a certified occupational hygienist and was SIMTAR's Principal Hygienist for approximately 9 years to July 2018. In mid-2018, Greg took up a role with Resources Safety and Health Queensland as an Inspector of Mines, initially evaluating the management and control of respirable dust and crystalline silica exposure in small to medium mineral mines and quarries. Just a reminder that this session will be recorded and it will be uploaded to the AIOH website in the coming days. We will take questions after the presentation. And you can post a question by typing into the Q&A function, or alternatively, if you want to chat with each other, you can use the chat function. So questions go in the Q&A. So over to you, Greg, for your presentation.
Thanks, Kelly. Thank you very much for that intro. You've just about covered all the material that I was going to cover, so it should make my job a little bit easier. I'll just get the slides up. You can see the presentation on screen now.
Yes, we can, Greg.
Yes.
That's perfect.
Okay. So I'll just get the screen working. Before we start, I'd like to acknowledge the contributors to this project, the Resource Safety and Health Coal Mine Inspectors, Fritz Dukic and Andrew Batterson. And you'll see some photos of those guys in action a little later on in the presentation. Our suppliers, DSI Underground, Wilson Mining and Minova, who very generously provided personnel, equipment, materials and time and location for us to do this testing. And the 4 laboratories that contributed to the analysis, SIMTAR's SGS, Queensland Health Forensic Sciences, and ChemSem Western Australia. I just need to point out the presentation is not intended as a promotion for the asset samplers. They just turned out to be probably the most effective for the project that we're doing. What's in the webinar? There'll be some information on isocyanates, uses, toxicology, and a bit of the chemistry. I'll talk about the history of our project and the state, the status at the moment. We'll look at some sampling methodologies and issues with exposure monitoring. We'll talk about the findings, what we found that we expected to find, and what we found that we didn't expect, which is the key to this presentation. And I'll look at some conclusions, issues, and recommendations. What I'd like to do before we dive into it is throw out an invitation for comments. I'm not a trained chemist. My knowledge just comes from smarter people showing me, or from texts and internet. So I'm keen to know what I don't know. So if anybody out there watching the webinar has observations or comments on anything in the webinar that might assist us to do it differently or better next time, I'd invite those comments. You can either do it through the session, or the last slide has contact details for Fritz, Andrew and myself. So you're welcome to get directly in touch with me if you prefer that. So let's dive into it. Isocyanates are a low molecular weight group of organic chemicals that are highly reactive due to the presence of one or more cyanate functional groups. That's this NCO, nitrogen, carbon, oxygen group here in the screen. They're widely used in manufacture of plastics and polymers, paints, rigid and flexible foams, insulation material. They're quite widely used in industry. And they're powerfully irritating, particularly to the respiratory system, but also the eyes and skin and gastrointestinal tract. Exposure can lead to sensitization of an individual, and this is they're noted as sensitizing agents. And the outcome of that can be potentially severe asthmatic reactions from continued exposure. And that exposure doesn't have to be very significant. It can be at very low exposure levels for a sensitized person. So they're quite hazardous to long-term health. Exposure routes are inhalation and dermal absorption. So the isocyanates can be readily absorbed through the skin. And I'll touch on that as we go through the presentation. Some definitions of terms that might be helpful, terms that I'll use during the presentation. So an isomer is two or more compounds that have the same chemical formula, but a different structure, different atomic structure in the molecule. And that causes even that potentially different physical and chemical properties. A polymer is a substance that is made up of repeating similar units. One that you'd be familiar with could be polystyrene, is a commonly recognized polymer. And oligomer is a term for a short chain polymer. So repeating units, but relatively few, generally between 3 to 10 repeating units is an oligomer, but it's just a short chain polymer. Isocyanates, just some articles I was looking at just within the last couple of days. Isocyanates are still recognised as probably the most common disease caused by prolonged exposure to isocyanates, and still a leading cause of work-related asthma. So hazardous. The most common form of isocyanate that is encountered commercially are the di-isocyanates. As the term suggests, they have two reactive groups in the basic molecule. Common ones are methylene diphenyl diisocyanate, or MDI, which Kelly mentioned earlier on. Toluene diisocyanate, hexamethylene, and their oligomers, or short chain prepolymers. You'll notice their MDI has three isomers, three common isomers, and toluene diisocyanate has two. Less common forms of cyanate containing chemicals are the other diisocyanates like naphthalene and isoflurane, but there are also the monoisocyanates, so molecules with a single cyanate group. The smallest is isocyanic acid, which is just the NCO with a hydrogen attached. but key to this presentation is the methyl and phenyl isocyanates. In mining, polymerics, so various different polymerics, and the isocyanate containing ones are split into two groups: polyurethanes, or PUR, and urea silicates. In mining, they're predominantly used for ground consolidation, so injecting into strata to stabilise it, fill cracks and bind the material together. Water control, and sometimes void filling. The key to risk management using polymerics in underground coal is that the isocyanate-based polymerics, particularly polyurethane, is exothermic during curing. They can generate quite a lot of heat, and particularly a risk when they're near coal with timber. There's a couple of links at the bottom of this slide to historical fires, underground fires that have a connection with polyurethanes, and the Westcliff fire, bottom there, was directly due to a large block of polyurethane that was curing and generated enough heat to set itself alight. So they are a fire risk as well as mutilation risk. A little bit on toxicology. Fundamentally, any molecule with the cyanate reactive group should be considered hazardous. And Soapwork Australia have recognised this in their documentation from their recent workplace exposure limit review that looked at isocyanates. The documentation states in part, and I've put some inserts here, that isocyanates have the NCO group, which is mechanically linked to the mechanistically linked to the sensitisation. Importantly, the Soapwork Australia documentation states that there's no difference in potency for different isocyanates based on the available epi data. So they're saying that anything with MCO should be treated as equally hazardous. And further, they stated that pre-polymer aerosols have the same ability as monomers to cause adverse effects. So it's critically important that any assessment of exposure risk is based on an accurate measurement of all NCO exposure as far as practical. Assessment should be all isomers, all monomers, all polymers of all species, if it's going to get you close to an accurate measurement. But the chemistry is a bit problematic. So, for example, MDI has 3 different isomers, and there's a diagram showing them. You can see the isomers. The only difference between the isomers is the location on the benzene ring of the NCO reactive group. But there are 3 different isomers. 4,4, the top one, is the most common, but the other 2 isomers can also be present, but current airborne and biological monitoring processes don't look for evidence of those 2 lesser or less common isomers. MDI oligomers and prepolymers are pretty much the same. The current methodology doesn't look for the short-term prepolymers of MDI. It only looks for MDI. Now, that's not all monitoring analysis, but most of the analysis at the moment doesn't identify those, and I'll touch on that further in the program. Critically, the chemistry of the initial molecule determines the form of the analyte that air monitoring analysis looks for, and the analyte that urine sampling looks for. So the analysis looks for a specific derivative of a specific isocyanate molecule. And that's where one of the limitations in the current risk assessment methodology is. I'll touch on our project and give you a little bit of background on that. Initially, the project was intended to look at potential exposures during polymerics, isocyanate-based polymeric sampling. We looked at two different sampling methods, the 37 ml treated filters and the asset samplers. And it was one supplier, one product, and we collected about 30 odd samples. The sampling was done at the supplier's factory, and it was in headspaces of containers. I'll explain a little bit of that because it's key to the context of the outcomes. There was some limited sampling at an underground coal mine during application and surface spraying, and we used a couple of photoionization detectors to sniff around to see whether there were VOCs emitted during the curing of the substances. Key outcomes from that very first stage were that we detected unexpected organo-isocyanates, and the PIDs showed that there were volatile organics in the air, but didn't speciate them. In visual form, essentially what we found was MDI, which we expected, but what we didn't expect was the phenyl isocyanate MDI oligomers, methyl isocyanate. So think Bhopal incident with regards to methyl isocyanate and propyl isocyanate. You'll see that each of those molecules has the NCO reactive group attached, and this is where the concern is. The next stages of the project were some further testing conducted at SIMTARs, which again used asset samplers, but added in various VOC sampling methods, sumicams and sorbent tubes and filters, to try and identify the VOCs that might have been there. That testing confirmed the presence of phenyl and methyl isocyanate in those prepolymers, and also identified some specific VOCs, chlorinated hydrocarbons, benzene and dioxane. So that testing then led to some more intense testing in September of 2020, which was designed to both confirm the initial findings, but also look wider across industry to see whether it was consistent or whether it was just related to that one substance from that one supplier. We collected about 150 odd samples from 8 products provided by 3 major suppliers to Queensland Coal, Queensland New South Wales Coal, and tested through 3 different scenarios up top point there. And we also ramped up the VOC sampling and analysis during the mixing and curing of the substances. Just before I get on to the results, I'd like to touch on the exposure monitoring process and where there's an issue in relation to isocyanates. So if I was asked to measure an exposure to a chemical, this is basically the process that I've go through. Identify using the label of the SDS the product being used or what the likely analyte or contaminant is that might be of concern. In this case, it was 4,4-MDI, which has its own CAS number, chemical abstract system. You'd research a method, and that's either, I suppose, internet searching. You'd look at OSHA and NIOSH or MDHS methods. SKC catalogue might point you in the right direction, or other reference material. And once you have your method, you'll collect your samples and send them to a lab. With regards to isocyanates, some of the problems with that process that we found are these. It's hard to know what was in the mix initially. So we assumed that it was 4,4-MDI was the substance that was being used. The MAK collection documentation back in 1997 talks about the MDI and polymeric MDI potentially containing contaminant phenyl isocyanate. And our findings confirm this. However, the MAK documentation goes on to say that these days the level of phenyl isocyanate is pretty low and so is irrelevant to health effects. Our findings suggest that this may be inaccurate and misleading. Some of it has to do with how the substance behaves. In this case, the liquid that we were looking at has multiple components. The majority of the components are 4,4-MDI or polymeric MDI, which has an extremely low vapor pressure. 1 millipascal is the vapor pressure for 4,4-MDI, which makes up the bulk of the liquid. Phenyl isocyanate has comparatively a vapor pressure about 200 times higher than methyl isocyanate, than the 4,4-MDI. And methyl isocyanate, again, is orders of magnitude greater. Simplistically, it's 54,000 times higher vapor pressure than 4,4-MDI. So the key here is that a very minor component in a liquid might unexpectedly be a major component of a vapor above the liquid. So it's important to understand that. I'm just going to duck back. I think that we might have missed a slide. Yeah. So this was a slide that I must have hit the enter button twice because you jumped over it. But looking at MDI, BASF is a manufacturer of MDI, and they produce a handbook that has some information in it. Essentially, 4,4-MDI is a solid at room temperature, and they turn it into a liquid by adding in one of the other isomers, 2,4-MDI, and some short-chain polymerics, which converts it into a liquid. There's no mention in the BASF information about phenyl or methyl isocyanate. The MAK documentation, which should have led into that other slide, talks about polymeric MDI containing up to 80% MDI, and then the rest of it is made up of those higher weight short chain prepolymers. We covered vapor pressure. Labelling is an issue. We found these are excerpts from labels from 3 of the safety data sheets that the suppliers were able to provide us. And you'll notice here that each has an ingredient listed with a similar CAS number. That CAS number is for polymeric MDI. But you'll notice that each of the SDS has a very different name for that CAS number. Well, not very different, but different enough to look like a different substance. Only one ingredient on any of the safety data sheets included the common name for 4,4-MDI and the CAS number. But there was no mention on any of those SDS of the contaminants or impurities. So this is intended to give you an idea of the potential complexity of the chemical and the lack of information that you might find on labels and SDS about what might be in the chemical. There's a link at the bottom of this particular slide to the Wiley online library that lists 18 different synonyms for MDI. So it's more complicated than what's just on that screen. With regards to a sampling methodology, we use 3 different sampling instruments for isocyanates. This one was the standard 37 ml treated filter. They're pre-treated during manufacture. They've got a reasonably limited shelf life. It's a single filter that collects vapor in a particular phase, but they're very robust and easy to use, very simple to use, good flow rate, and they've got a good sample duration range in the method. So you could do still for full shift, but the analysis, the analytical range is quite limited for this. The second sampling media that we used for isocyanates was the IsoCheck. Again, SKC. It's a dual filter cassette, one filter for particulate, one for the vapor phase. The trick with this one was that the particulate filter needs immediate removal post-sampling to be placed into a jar of derivatizing fluid, and then everything's got to be resealed and wrapped in alfoil afterwards. The samplers are quite easy to use and robust. They're just complicated by that transfer of the filter in the field, but the flow rate again was pretty good. Method talks about a 15-minute sampling duration, but we sampled for longer in the field because we weren't particularly worried about overloading. This sampler also has limited analytical range. The third type of sampler we used was the asset easy for NCO samplers by Sepulchre. They've got two different collection media in them, one for vapor and one for particulate. And they're a little bit trickier to use than the 37 ml filters. We needed to use low flow adapters, which then ran into some issues with regards to the atmosphere in the headspaces we were testing in. But they have a much broader analytical range than the other sampling methods. They're a little bit delicate. I was a bit of a dunderclumping and broke a couple in the field, but they don't require refrigeration either before or after sampling. So they have some upsides and some limitations. The key is that they have a much better analytical range than any other method. The fourth type of sampling method that we used were the sumer canisters for volatile organics. They're an environmental sampling method, looks for a very wide range of VOCs using the US EPA analysis method. And essentially it's a stainless steel can under vacuum, very simple to use, crack the valve, it sucks the sample into the can. You can use a regulator if you want to sample over a period of time, but the sumer cans were very easy to use, and there'll be a picture of one of those being sampled shortly. I have to issue a caution in terms of the context of this sampling. This was headspace testing, so essentially it's collecting the sample from inside the enclosed space above a liquid inside a container. It's worst case emission sampling. We were looking at quantifying concentration so much as just identifying what was there. So vapor saturation was our goal. And there's no ventilation in that space. So these results must be looked at in the context of the sampling conditions and the purpose of the sampling. Workers wouldn't normally be expected to be exposed to these conditions. With the spill simulation also, it was a large surface area and sampling was done very close to the spill or the simulated spill. So again, not intended to be representative of the exposure. Always good to have some pictures. This is, you can see Fritz hard at work setting up some samplers on the left-hand side there. Photo in the middle shows the spill simulation at one of the providers. Basically, we cut out opposite sides of a sacrificial IBC, put the MDI liquid in the base of the container, had a fan here blowing air across the liquid, onto the samplers, which were positioned about 30 centimetres away from the liquid surface. This photo here on the right is looking down through the opening of an IBC. You can see the polymeric material there curing, foam, expanding foam curing. This is a sample array. And you'll see the layout of the sample array in the next slide. But essentially, that's a 37 mil treated filter, an asset sampler, and this is an ISO check. The piece of 1/8 stainless steel tube sticking through the side here is a Summa canister sample being collected. The sampling arrays were set up. This is an IBC headspace testing. You can see the liquid level in the bottom. That will be neat MDI. And the sampling was done with triplicate sets of each of the 3 samplers. You can see there's a treated filter, an ISO check, and an asset sampler here. There's another set there and another set there. So each test consisted of 9 samples, which is triplicates of each of the 3 sampling types. Regarding the emissions, or the outcome, the neat MDI testing found phenyl and methyl isocyanate in all formulations from all suppliers, and generally in greater concentrations than the MDI. So I'll take you back to that vapor concentration issue. The methyl and phenyl isocyanates were at very, very low concentrations in the liquid, but proportionally were much higher concentrations in the vapor. So it's really important to know what's in the chemical as a liquid and what might be in the vapor above the liquid. Sampling found MDI monomers and prepolymers, and the assets were the most reliable and sensitive sampling method from these tests. With regards to the mixing and curing, so you can see their pump operator is pumping into the IBC a combination of the MDI and the other agent and mixing it. And again, we found phenyl and methyl isocyanate in every formulation. Again, generally at greater concentrations in the MDI. So the overall result of that testing, the sampling that we did there, was that we found a lot of contaminant isocyanates that were only identified using the asset samplers. We would have missed them had we just been using impinges or treated filters. In the emissions from simulated spills, again, phenyl isocyanates were in the emissions from all 3 tests, and the asset samplers were again the most reliable. The results indicated that the emissions from a potential spill or from a spill underground, the inhalation risk looks to be relatively low. So a summary of what we found from the mixing and curing tests. You can see there we found the target analyte for MDI on all the asset samplers and most of the treated samplers. Phenyl isocyanate was found on every sample, and methyl isocyanate was found on, what's that, 34 out of 38 samples. Key here is that the only reason we found these phenyl and methyl isocyanate was with the asset samples. Here's a bit of a visual summary of some of the findings. You can see on the left these are the tests for the neat MDI, different suppliers, and we found phenyl and methyl isocyanate in everything, and in the mixing and curing, phenyl isocyanate and methyl or MDI prepolymers in everything. So that was the surprise that that has brought about this this further testing was these unexpected organo-isocyanate. In the spill testing, pretty much the same, although the key here is that 4,4-MDI was found on all the assets, but not on any treated filters. So as the concentration reduced, the asset samplers were more precise than the treated filters. And that's, you can see that on this one here and one below. One thing we did find was that with the as the concentrations reduced, methyl isocyanate started to disappear from the asset samples. With the VOC emissions, that's Fred's collecting a Sumacan sample. There were low levels of multiple VOCs detected. So halogenated, bromo and chloro hydrocarbons, there was acetone and ethanol and some other substances, and qualitative detection of a range of other volatile organics. The emphasis here is that there was detection, but it was all at low levels. When I say low levels, there was no single VOC result that was above the relevant ARWES, and this was all headspace testing. So the VOC levels were low, but they should be recognised as being there and maybe consider the potential additive effects from multiple VOCs in airspace. Just touched on those. The headspace testing, workplace exposure levels would be much lower than, should be much lower than what we measured. Importantly, there was no single VOC that consistently showed up that could be used as a surrogate for risk evaluation. And this is because each of the mixtures contains different chemicals. They all contain the MDI, but what they're being mixed with can be very different. And that is what drives the VOC emissions. So again, exposure to VOC should be low, particularly if ventilation is good, but consider that they are there and there are potential additive effects. Monitoring method issues. Most isocyanate monitoring methods use treated filters or impingers, recommend treated filters or impingers. But treated filters, the analysis is very limited, generally only the primary monomers. Impingers are fragile and present their own risks. And none of the methods, those traditional methods, look at these contaminant NCOs. The asset sampler, again, does a much greater range, looks at monomers and polymers, but it's not complete. It doesn't look at all of them. So, for example, SGS don't currently analyse for isocyanic acid, which is also potentially in the atmosphere. The asset samplers will collect it, but it's under the laboratory as to whether they analyse for it. So again, make sure that you understand, if you're collecting a sample, what your lab can and can't analyse for. Analytical methods we used were through SIMTAS for the treated filters, ChemCentre Western Australia for the ISO checks, SGS Melbourne for the assets, and Queensland Health for the Sumacans. But there are potentially issues with the analysis that I've touched on. You might have another lab accredited for isocyanates, but not necessarily analyse for all of the substances that you think of being analysed for. You may have another lab that does isocyanates, but it's not under their accreditation suite. But that's not necessarily a problem. NATA accreditation provides a high level of confidence in the quality and systems in a lab, but it doesn't necessarily guarantee that the analytical method is accurate for what you're looking for. I just want to touch on absorbed dose, or the combined risk from inhalation, potential skin exposure. Skin absorption is generally considered to be probably the greatest exposure source in underground mining, due to largely historical practices of sample handling. But skin absorption risk needs to be considered, particularly in Mexican cleanup. The issue with skin absorption is that the biological markers, looking for biomarkers in urine, only assess the metabolites for the primary diisocyanates, MDI, TDI, HDI, and probably methylene diisocyanate. There's no current assessment of biological markers for phenyl or methyl isocyanate. That may or may not be significant. There's a very low percentage of these in commercial MDI products. So there's a very small amount in the liquid. So skin absorption of these two may not be significant. The bigger risk might be from the 4,4-MDI and the prepolymers. But then you get into issues of solubility of the liquid in terms of molecular size. The larger the prepolymer, the less lipid soluble probably is. So the potential for skin risk is unclear from those substances. In terms of the absorbed dose, there have been some process improvements that have resulted in a reduction in the potential for skin exposure. Often these are regulated driven. An example is the move in underground coal mining in Queensland to 1,000-litre IBCs instead of the old process of manually tipping 20-litre drums into the pump tanks. The wider problem with that is that smaller drums equal potentially less waste. So a supplier is probably less likely to use a 1,000-litre bulky unless they are going to use a lot of material and waste less. So it's important. The key there is to assess the workplace and the handling processes to identify whether there's a skin exposure risk and control it. Just touch on current testing in Queensland coal mines. So historically, there's only been limited exposure testing, atmospheric exposure testing in coal mines, almost exclusively involving the treated filters, 37mm treated filters, with those limitations on analytical breadth. Exposure assessment in coals are mostly focused on skin absorption and biological monitoring. But despite the apparent low inhalation risk, there have been large exclusion zones legislated to prevent exposure to persons downwind of the application, which brings in its own problems. Excluding people from a certain area of a mine during maintenance can potentially impact on other safety issues such as consolidation of unstable ground and that type of thing. So the coal inspectorate initiated testing to better understand the inhalation and emission risk underground. This is where the current testing in Queensland coal is at. So we put together a sampling plan, which is essentially a protocol to have the testing done consistently and to collect enough data to make some evidence-based decisions on exclusion zones and exposure. The sampling plan provides detail on recommended methodologies for sample collection and analysis, competencies of persons undertaking and overseeing the sampling, and reporting requirements, what needed to be reported in terms of observations during the sampling. The goal was assess the inhalation risk to workers from personal sampling. So that was task specific, personal sampling, stills if practicable, and then ideally matched with pre and post biological sampling of the target workers if possible. And the second phase was assessing the exclusion zones with static sampling at set distances downwind of the application point. So we can get an idea of what distance from the application we were reliably not detecting any contaminants. This is some of the this is some photos of the tailgate warriors in action. You can see on the left-hand side is the static sampling setup with the sampler set at about 1.5 metres. Andrew Battison unkitting after some work underground, and Fritz just come up again from underground. The results from this testing so far are reasonably encouraging. There's been, you can see there's been testing on urea silicates and polyurethane, spray lining and injection, so different applications of different materials. Personal and static sampling, and most of the samples have been non-detects for isocyanate so far. The detects have all been less than 50% of the OEL and mostly less than 10%. So there's some reasonably good indications that while the contaminants are there, the level of exposure looks to be reasonably well controlled in underground coal. Now they've got some pretty significant ventilation controls in a lot of those situations. So the exposure being measured here may not be the same as exposure at, say, a spray painting workshop. I'd like to touch on the proposed changes that Safe Work Australia have suggested to the TWA and STEL for isocyanates. These are the proposed new exposure standards. They haven't been implemented as yet. I'm not sure whether they will be, but the links to the documentation for these are at the bottom of the slide. And you can see that isocyanates, so currently the exposure standard is isocyanates all as MCO. And Safe Work Australia have proposed separating that out to 3 different standards. One is isocyanates poly as MCO, which does not include any of the monoisocyanates. They were explicitly and deliberately excluded. It only includes the di and tri-isocyanates. And you can see there that the proposed exposure standard is a drop of from 0.02 to 0.0001, so a 200-fold reduction in the time-weighted average and removal of the STEL. They've suggested introduction of exposure standards, new exposure standards for phenyl and methyl isocyanate as the whole molecule. So you can see phenyl isocyanate, that 0.024 is the phenyl isocyanate molecule. I've calculated out what that would be as the MCO component to be able to compare with the other exposure standards. I really can't understand why the exposure standard for phenyl and methyl isocyanates is significantly higher than the proposed exposure standard for polyisocyanates, given that Safe Work Australia's documentation says that it should all be considered as hazardous. I really can't explain why that difference is there, but it is. So comments on the WES. The proposed changes haven't been brought in yet, as I said, but it illustrates the recognised hazard from the 2 main contaminant monoisocyanates that we found in our testing. And it illustrates the thought process that Safe Work Australia have regarding how low they think the WES should be, again emphasising the hazard level and the sensitisation risk. The emphasis is on that isocyanates, all as MCO, the current exposure standard, should cover as much of the MCO containing molecules as possible. That's monos, dis, polys, and all isomers. I'll just roll into some conclusions from that. And sorry that it's been a little bit intense up to this point, but conclusions that we've all this down to is that MDI contains contaminant isocyanates that are mostly more volatile than the MDI itself. But the contaminants are not clearly detailed in safety data sheets, so they're not widely recognised as being. Primary exposure risk is most likely skin absorption, but the current biological monitoring doesn't adequately identify all the biomarkers for contaminant from those other isocyanates. Most isocyanate air monitoring techniques are largely inadequate. They don't cover enough breadth of NCO containing molecules to give you a good overall exposure. And so the exposure risk is likely to be underestimated at present. A couple of other conclusions were that from our testing was that emissions from the spill simulation appear to be quite low, but they also contain VOCs, the emissions, and that also is not widely recognised. So it's not easy to identify the contaminants from in amongst the clutter of chemical names and CAS numbers. And as I've said, SDS and labels aren't clear. Air and biological monitoring processes aren't looking for everything that a worker might be exposed to, and VOC emissions are generally not recognised or measured. Some recommendations for occupational hygienists out there. Make sure if you're using a method, a sampling and analytical method, that you are aware of the limitations of the method and the analysis. Check with your laboratory and make sure that what they're analysing for will actually give you what you're looking for. Understand the chemical complexity of contaminants. An example of this is the chaos around the naming of isocyanates, but this would apply to many chemical groups. Consider the difference between proportions in a liquid phase and a vapor phase, and what the differences in vapor pressure might mean in terms of converting a risk of exposure from a liquid to a risk from a vapor. And it's important to assess, particularly with isocyanates, the potential for inhalation and skin risk, and be aware of those VOCs. With regards to analytical laboratories, I think there's a real opportunity here to review analytical methods and look to provide hygienists with the simplicity of a treated filter combined with the analytical range of the asset sample. I am unaware of what the technical difficulties could be in that, but the sampling should be able, there should be a method to sample using robust sampling equipment that doesn't need low flow adapters or special handling, with the analysis from the assets to give you the best outcome. With regards to suppliers, clearer identification of the potential contaminants is required in SDS and labels. I'm not suggesting that the SDS are non-compliant. It may come down to the legislation around SDS in terms of percentages of contaminant and whether it gets reported. But clearer information would certainly be helpful. And for users, be aware of the potential contaminants, and skin risk is probably the most significant of absorption. That's the end of the information in the presentation. Our contact details are there on that final slide, and I'd welcome any questions or suggestions that you might have. My contact details are there, so please make use of that if you need to.
Greg, thank you very much. What a fantastic and detailed presentation, and what a big effort RSHQ and yourself have gone to produce this body of work on isocyanates. And I think your recommendations at the end are really, very important for all hygienists, not just, as you say, for isocyanate monitoring, but other monitoring work that we do as well. Unfortunately, we've got like 1 minute left.
Yeah, sorry about
You've
that.
got-
That wasn't deliberate.
That's okay. You do have about 5 questions, I think.
Okay, yeah.
Yeah, 6 questions now. Look, I might have time for one quick question, and what we'll do is we'll take note of the other questions, and you
Sure,
may be
yeah.
able to post the answers to those questions with the recording online for those we don't get to.
Sure, the easiest question. Yeah.
The easiest. I'll just go with the first question. So Sage Robinson asks, did you look at using hazard vapor calculations to back convert the air concentration ratio of MDI, phenyl isocyanate, etc., to an expected liquid ratio, and see if this was in line with the literature documentation on low levels of phenyl isocyanate?
No, we didn't. I'd be interested in that process because I haven't used that. So I'd be quite keen for you to send me information on that process. We had a fair bit of difficulty getting any information on the proportion of different contaminants, the phenyl and methyl isocyanate, in the liquids. The providers were very happy to engage with us, but are very secretive about their mixtures, because each mixture is has a specific outcome or result, and that's their commercial edge, if you like. Even had we been able to calculate it, we had nothing to back compare it to, so we wouldn't have been able to match where the vapor, what the vapor concentration was expected to be. Now that I suppose touches on chemical aspects such as Ralph's law and Dalton's law of partial pressures, and it's unclear what reactivity and bonding there is in the liquid that enables the different subcomponents to become volatile. So short answer is no. The long answer is I'd really be interested in that process for future use. So thank you. That was a good one.
Greg, well, we've run out of time, but there are lots of thank yous for your presentation in the Q&A along with questions. So thank you from the audience, obviously, as well for your presentation.
I have been working on an alternative version delivered through sock puppets and interpretive dance, but that one's not ready yet, so you had to go with the bell.
I would love to see that, Greg.
I'd have to be drinking heavily for you to see that one.
I would say so. All right, well, we're up to 10 questions now. So as I said, we'll wrap up now. And Greg, you can provide some typed answers to those that we'll put up as a file along with the recording on the AOH website. So thank you everyone for joining us for our second webinar, and we hope to see you at our next webinar in April. So thank you again, Greg.
Thanks, Carl. Thanks, everybody.